So hello and welcome you all for yet another session of Restart. So basically we are in our 14th day, and yeah, we have 4 days left including today, and now it's gonna be nearly 10 o'clock of the day. So basically இன்னைக்கு we'll try covering 5 or 4 chapters. So I feel that reading மட்டுமே it's not going to be important. So நம்ம ரீடிங் பார்க்க வந்து we'll just skip it as quick as possible. I mean, not skip, we'll just skim through things because that we have already learned them. If solving questions is really really important, yes, so we'll have to make sure that we are solving questions. And yeah, so let's get started for the day. ஸோ நேற்று நம்ம எலக்ட்ரோஸ்டாட்டிக்ஸில் எலக்ட்ரிக் சார்ஜஸ் அண்ட் ஃபீல்ட்ஸ் அப்படின்ற அந்த பர்டிகுலர் சாப்டரை கம்ப்ளீட் பண்ணோம். நவ் வி ஆர் என்ட்ரிங் இன்டு எலக்ட்ரோஸ்டாட்டிக் பொட்டன்ஷியல் அண்ட் கெப்பாசிட்டன்ஸ். ஸோ எலக்ட்ரிக் பொட்டன்ஷியல் டிஃப்ரென்ஸ், எலக்ட்ரிக் பொட்டன்ஷியல் டியூ டு பாயிண்ட் சார்ஜ். ஸோ எலக்ட்ரிக் பொட்டன்ஷியல்னால் என்னன்றது டிஃபைன் பண்ணுவோம். and then potential difference என்னன்றது, and then potential due to point charge, a dipole, system of charges, equipotential surfaces என்ன, and electrical potential energy na enna, since it is a conservative force, conservative field is associated with a potential energy, and potential energy for 2-point charge systems, and then we'll have an electric dipole and an electrostatic field. And then after we complete all these things, we will enter into capacitance. But before that, we will define what a conductor is, insulator is, what are free charges, what are ground charges inside a conductor itself. And then we'll talk about dielectrics, electric potential, polarization, and then we'll enter into capacitance combination, capacitance of parallel capacitor with and without dielectric medium, and then finally we'll have the energy stored with no derivation it seems. So it's rather not a tough chapter. Yes, it can be completed, I hope. So as I said, I will be using the old textbook only, so that it will be better. Yes, electrostatic potential and capacitance. Okay, so that's the chapter. We will not check the pages. Okay, so if I am seeing the pages, then I will get irritated or get upset. So we'll go one by one according to the topics that has been indicated. So first things first, introduction. In chapter 6 and 8, the notion of class 11, the notion of potential energy was introduced. So basically we were talking about the work power energy chapter, in which we came across potential energy. When an external force does work in taking a body from a point to another against a force like spring force or gravitational force, that work gets stored as potential energy of the body. So when the external force is removed, the body moves, gaining some kinetic energy and losing an equal amount of potential energy. The sum of kinetic and potential energies is thus conserved. Forces of this kind are called conservative forces. The spring force and gravitational force are certain types of conservative forces. So first things first, the first paragraph itself, they are saying what a conservative force is. So basically for a conservative force, the mechanical energy is always conserved. That is, the sum of potential energy and kinetic energy is always conserved, and for such type of fields only we will have potential energies. And basically potential energy is the amount of, it's the work that we are doing against let's say a force that's acting in that particular region, to in which this particular work is getting stored as a potential energy, and as soon as the force is removed, it will be moving, the body will be moving with gaining certain amount of kinetic energy. Okay, so why are we talking about this? Let's move on. Coulomb force between two stationary charges like the gravitational force is also a conservative force. So Coulomb force என்பதும் it is a conservative force அப்படின்னு சொல்லுவாங்க. This is not surprising since both the inverse square dependence on distance and differ mainly in the proportionality constants only. The masses in the gravitational law are replaced by the charges in the Coulomb's law. Thus, like the potential energy of a mass in a gravitational field, we can define electrostatic potential energy of a charge in an electrostatic field. So basically Coulomb force அப்படின்றது it does have an basically it is conservative of nature, which as it is gravitational force அப்படின்றது it is conservative in nature, and both these are related to each other in a more similar manner, that is both are inverse square laws. And then we have the proportionality concerns are obviously different, and then we have the charges to be different as well. I mean, charges or masses are the counterparts of each other. So basically we can define electrostatic potential energy for charges in an electric field. So consider an electrostatic field E due to some charge configuration. Okay. First, for simplicity, consider the field E due to charge capital Q placed at the origin. Okay. For simplicity, now we are considering a charge capital Q that is being placed at the origin. Now imagine that we bring a test charge small q from a point capital R to a point P against the repulsive force on it due to the charge capital Q. So it does mean that basically these guys are actually of the same type of charges, which means they will repel each other. So with reference to figure 2.1, this will happen if capital Q and small q are both positive or both negative. So it will be in such a case scenario when both are of like charges. In such case scenario, we will have a repulsive force acting on the particular small q, and the work we are doing will be against that particular repulsive force. For definiteness, let us take capital Q and small q greater than 0. Okay, fine, great. So two remarks may be made here. First, we assume that the test charge small q is so small that it does not disturb the original configuration. So since the small q can have an ability to displace the capital Q due to its repulsive force, what we are assuming is that this small q is having a very small size or the properties are really smaller in compared to that of the capital Q charge, such that the configurations are not changed. That's the first assumption that we'll have to do, or else we will keep the capital Q fixed at the origin by some unspecified force, which is not going to be irrelevant. So it would be better to take small q. Actually, it's not that irrelevant in சொல்ல முடியாது, but yeah, it would be better. So second, in bringing the charge small q from capital R to capital P position, we apply an external force F external just enough to counter the repulsive electric force. Okay. So what we will do is that we will just counter the repulsive electric force, which means that the external force that we are going to apply will be exactly equal but opposite in direction to that of the electric force that is being applied due to the particular capital Q charge. This means there is no net force on or acceleration of the charge small q when it is brought from R to B. That is, it is brought with infinitesimally slow constant speed. So இப்போ இதுக்கான என்ன அர்த்தம் அப்படின்னா, basically there is no net force acting. Next external force are all cancelling out each other. Yes, and which means that it is coming with very small speeds, infinitesimally small speed அப்படின்னா it is barely moving with respect to time ன்ற மாதிரியான ஒரு situation. So in this situation, the work done by the external force is the negative of the work done by the electric force. ஸோ அதாவது எலக்ட்ரிக் ஃபோர்ஸ் என்ன ஒர்க் பண்ணுதோ அதோடைய நெகட்டிவ் ஒர்க் தான் வந்து ஒர்க் டன் பை த எக்ஸ்டர்னல் ஃபோர்ஸ். ஆப்வியஸ்லி பிகாஸ் we are both in equal magnitude and opposite in direction, and they are both doing the same things in the opposite sense, which means that it will be a negative of the electric force at a work done, and gets fully stored in the form of potential energy of the charge q. So if the external force is removed on reaching P, the electric force will take the charge away from capital Q. அதாவது if I'm removing the external force that is acting on reaching P, the electric force will take the charge away from Q, and the stored energy at P is used to provide the kinetic energy, and in such a way the sum of the kinetic and potential energies are conserved. So that's work done by external forces and moving charges from shifting it from position R to P is in integral of F external dr for every differential element from R to P, which is also equal to negative of the work done by the electric force, electric field or whatever, from taking the guy from R to P. So this work done is against the electrostatic repulsive force and gets stored as the potential energy. At every point in electric field, a particle with charge small q possesses a certain electrostatic potential energy. This work done increases its potential energy by an amount equal to the potential energy difference between the points R and P. அதாவது ஒவ்வொரு பாயிண்ட்லையும் ஒரு ஃபீல்டுன்னு எடுத்துக்கிட்டோம் அப்படின்னா, if let's say I have a charge q, in the charge q will have certain amount of electrostatic potential energy in each point, and then which means that the work done increases its potential energy, and basically the potential energy difference will be that equal to the potential energy at position P and potential energy at position R, and since we cannot define exact potential energy potential values, so we will be able to calculate potential energy differences, and this potential energy difference turns out to be equal to the work done in moving the particular point charge from R to P. Hope you are able to understand that. Yes. So basically this work done increases its potential energy. Okay, so potential energy or a difference will be equal to the whatever the amount of work you are doing. So note here that this displacement is in an opposite sense to the electric force, and hence work done by electric field is negative. அதாவது at this particular point the displacement is in an opposite sense to the electric force. Okay, and hence work done by the electric field is negative. Okay, fine. So therefore we can define electrostatic potential energy difference between 2 points as the work done required to be done by an external force in moving without accelerating a charge q from one point to another for electric field of an arbitrary charge configuration. So how are we defining electrostatic potential energy is that electrostatic potential energy of a system, okay, potential energy difference between 2 points is considered as, so we will define for between 2 points. Okay, rendu point nadulla the electrostatic potential energy is considered as the difference or as the work done in by an external force, work done by an external force in moving that is without accelerating. So it is moving with infinitesimally small speeds. Why? Basically the external force is exactly equal in magnitude to that of the external field, and which means that the net force is actually 0. So there is no acceleration occurring. Moving with infinitesimally small amount or moving without acceleration, acceleration of the charge q from one point to another. For electric field of an arbitrary charge configuration. For electric field of an arbitrary charge configuration. Okay, fine, great. So let's say there are two important comments may be made at this particular stage. The right side of the equation 2.2. So what was that? That's the work done from shifting the guy from R to B depends only on the initial and the final positions of the charges. So as you can see, it only depends upon the initial and final position. We are not at all talking about, okay. So it means that the work done by an electrostatic field in moving a charge from one point to another depends only on initial and the final points and is independent of the path taken. Right. So this is the fundamental characteristic of a conservative force. அதாவது கன்சர்வேட்டிவ் ஃபோர்ஸை பொறுத்த வரைக்கும் என்ன மேட்டர் அப்படின்னா, ஒரு பொட்டன்ஷியல் எனர்ஜி அப்படின்ற ஒரு கேல்குலேஷனை பொறுத்த வரைக்கும் it should not depend on in which path you are basically taking it. Whatever the path you are taking it, if at all there is a certain initial and final position, it is going to depend only upon that two particular points. So this is the fundamental characteristic. The concept of the potential energy would not be meaningful if the work depended on the path. The path independence of the work done by an electrostatic field can be proved using the Coulomb's law, but we are omitting this proof. So what they are saying is that there is a path independence of this particular work done by an electrostatic field, and it can be done by using Coulomb's law, but okay, great, fine. So equation 2.2 defines potential energy difference in terms of the physically meaningful quantity work. So clearly potential energy so defined is undetermined to within an additive constant. What this means is that the actual value of potential energy is not physically significant, it is only the difference of the potential energy that is significant. We can always add an arbitrary constant alpha to the potential energy at every point, since this will not change the potential energy. So அதாவது potential energy அப்படின்ற difference is actually signified more relevantly with respect to that of the work, which means that potential energy or position amount of potential energy is irrelevant for me. What's going to be relevant is that the change or the difference in the potential energy at the two particular configurations. So which means that whatever the constants you are adding at every point, it's not gonna matter, as they are gonna get whatever the subtracted out. Yes. So put it differently, there is a freedom in choosing the point where potential energy is zero. A convenient choice is to have electrostatic potential energy zero at infinity. ஸோ அதாவது பேசிக்கலி ஒரு பர்டிகுலர் பொசிஷனில் வந்துட்டு இஃப் வில் ஹாவ் டு டிஃபைன் அண்ட் பொட்டன்ஷியல் எனர்ஜி விச் இஸ் நாட் ஆக்சுவலி பாசிபிள், பட் ஆல் யூ கேன் டூ இஸ் டிஃபைன் த டிஃப்ரென்ஸ் இன் பொட்டன்ஷியல் எனர்ஜிஸ், விச் மீன்ஸ் தட் ஒரு கான்ஃபிகரேஷனில் இஃப் ஐ ஹாவ் பொட்டன்ஷியல் எனர்ஜி ஈக்குவல் டு ஜீரோ, then obviously I can say the potential energy with respect to that particular position, and it would be always convenient to take at infinity the potential energy to be equal to zero. So which means that work done in moving a particular charge from infinity to, let's say, a point P is equal to the potential energy at position P minus potential energy at infinity, and we consider the potential energy at infinity to be equal to zero. So since the point is arbitrary, equation 2.3 provides us with a definition of potential energy of a charge q at any point. So until P is going to be arbitrary, which means that I can define potential energy at any point. I'm not constrained it to be at particular position or particular configuration. I have defined it for every point or any point. So which means that it is applicable for every point. So potential energy of a charge q at a point in the presence of a field due to any charge configuration is the work done by the external force in bringing the charge small q from infinity to that point. So how are they defining potential energy of a charge q is that it in the presence of an what obviously in the presence of an electric field is basically the work done by an external force in bringing the charge q from infinity to that point. So that's how we are actually defining the potential energy of that particular charge q or particular point. So இதுக்கு முன்னாடி we define the potential energy difference as the work done by an external force in moving a charge q from one position to another, and if I will have to define for potential energy at one particular point, then I am considering the other point to be equal to zero. I mean the potential energy at other point will be equal to zero, such that I am defining it as the work done by an external force in bringing that particular guy from infinity to P. Thereby I am getting the potential energy at P. Yes. So that's how we are defining potential energies. Moving down, we will talk about electrostatic potential. So consider any general static configuration. We define the potential energy of a test charge q in terms of the work done on the charge q. So this work is obviously proportional to small q, since the force at any point is equal to q into E, where E is the electric field at that particular point. It is therefore convenient to divide the work by the amount of charge q so that the resulting quantity is independent of q. In other words, the work done per unit test charge is the characteristic of the electric field associated with the charge configuration. அதாவது என்ன சொல்ல வராங்கன்னா, as we have seen, the work done is obviously directly proportional to whatever the amount of charge q you have taken, as the amount of force is actually equal to q into E, and q into E into dr integral will always be directly proportional to the charge q, and charge q is something which is constraining something. அதாவது அந்த பர்டிகுலர் சார்ஜோனால that is the amount of work done அப்படின்ற மாதிரி சொல்லும் பொழுது it would be better if I am defining a new quantity. அதாவது physics if I am defining a new quantity அப்படின்னா it will be definitely useful, and that's why I am trying to define a new quantity such that I am taking out the picture of a charge q itself from this particular force, so that I am making it independent of anything else and making it dependent only on a particular another factor, that is the electrostatic field. So in other words, the work done per unit test charge is the characteristic of the electric field. அதாவது I am defining something with respect to the electric field அப்படின்னா it should be dependent only upon the electric field intensity, which means that I will have to take everything else out of the picture. So I am dividing it by q and making it such that the work done by unit test charge is the characteristic of the electric field associated with the charge configuration. This leads to the idea of the electrostatic potential due to a given charge configuration. So let's say I have been given with the charge configuration, which means that I will define certain factors, parameters for that particular charge configuration, அதோடைய field, such that the work done by the unit charge whatever is equal to the electrostatic potential. So basically, the work done by external force in bringing a unit positive charge from point R to P. The work done by external force in bringing a unit positive charge from R to P, basically I'm defining it as the potential difference. That is, let's say the potential at Vp, V at P and potential at V at R is actually defined as the work done per unit charge, and work done is obviously equal to the difference in potential energies for that particular conservative field, which means that I'm defining it as the potential energy at P minus potential energy at R divided by the amount of charge Q. And that's how we are defining the work done by external force with respect to the electrostatic potential, where Vp and Vr are the electrostatic potentials at P and R respectively. Note, as before, that is not the actual value of potential, but the potential difference is physically significant. So we will not have anything significant with respect to the potentials actually, but it would be significant if we know that potential difference, as it is actually the work done per unit charge. Work done is actually something physical, and if the difference in potentials are equal to something physical, then obviously that will be considered more important or more importance in physics as far as we are concerned. So if, as before, we choose the potential to be 0 at infinity, then the work done by an external force in bringing unit positive charge from infinity to a point is what we define as the electrostatic potential at that point. So first எப்பொழுதுமே we will define something relevant and we will make certain modifications, and அதை வச்சு தான் we are trying to calculate the electrostatic potential at a given particular configuration. So what is it? It is the work done by an external force in bringing a unit positive charge from infinity to a point. So how did we define potential energy is that the work done by an external force in bringing a charge Q from Q to infinity, but here we are talking about bringing a unit positive charge, which means that we'll have to divide the configuration with the amount of charge which I am bringing. Yeah, that's it, that's all about it. So let's say, in other words, the electrostatic potential at any point in a region with an electrostatic field is the work done in bringing a unit positive charge from infinity to that point. We are talking only about a unit positive charge, which means that with respect to the amount of charge you are taking, the amount of work done is going to vary, and with respect to that, the potential will obviously be varying. So the qualifying remarks made earlier regarding the potential energy also apply to the definition of potential. நம்ம என்னென்ன சில ரிமார்க்ஸ்லாம் பண்ணோம், to obtain the work done per unit test charge, we should take an infinitesimal test charge, first thing. Next, and also the external force at every point of the path is equal and opposite. So we are taking an infinitesimal point charge with this infinitesimal in all respects, and then we are considering the external force at every point to be exactly equal in magnitude that of the electric force that is being produced due to another charge, let's say Q or whatever it is. So as you can see in the figure 2.2, the work done on a test charge small q with electrostatic field due to any given charge configuration is independent of the path. That whatever the work you are going to do, it is going to be independent of the path. All it's going to depend upon is only on the initial and the final configurations. Moving down, we are talking about potential due to a point charge. So consider a point charge capital Q at the origin. Okay, so I'm basically considering a point charge Q at the origin. Yes. And yeah, I would actually suggest you all to take a note and a pen so that it will be easier for you to just write certain things so that it will be useful in later parts. Yes. So for definiteness, take capital Q to be positive. I don't know what the fascination of them to be taking that particular thing as positive. Fine, great, let's take it as positive. We wish to determine the potential at any point P with position vector R from the origin. So let's say I have a point P which is at a distance R from the origin, which means that its distance from the point charge is going to be R. Yes. So for capital Q greater than 0, that is for a positive charge being placed at the particular origin, the test charge is positive. Since work done is independent of the path, we choose a convenient path along the radial direction from infinity to the point. So I am trying to calculate the potential due to a point charge. So potential due to a point charge basically what I am trying to do is creating an electric field, and I am taking a test charge and I am considering a path. Basically the work done is going to be independent of the path. So work done we are actually trying to calculate the work done, and potentials are actually going to be dependent upon the work done, which means that I will not have to choose, we can choose, we are free to choose any random path, and I am choosing the simplest path, that is the radial direction, path in the radial direction. So basically we are choosing a convenient path along the radial direction from infinity to point P. Yes. So at some intermediate point P dash on the path, the electrostatic force on a unit positive charge. Okay, so basically I'm calculating the electrostatic force. Force at a unit positive charge is K Q into unit positive charge, which means 1 by R square R dash cap. Okay, whatever. So at certain intermediate part, I do not know the position of the path. So at that particular part, the electrostatic force is going to be equal to Q into 1 by 4 pi epsilon naught times R square, where R dash square is the unit vector along OP dash. So work done against this force from R dash to a slightly differential element delta R. So let's say I've got this guy to a position at R dash position, okay, and moving it for a differential amount, how much is the work done is going to be equal to the, so delta W is minus Q by 4 pi epsilon naught times R dash square delta R dash. So basically it is the force multiplied by the amount of distance that you have traversed. Yes. So the negative signs appears because for delta R dash less than 0, that is, it's not possible actually, but the delta R dash less than 0, the delta W is going to be positive. Total work done W by the external force is obtained by integrating R dash from infinity to that particular configuration of R. So ஒரு infinitesimal amount of movement the amount of work done is going to be equal to negative of the force that is being exerted on the unit positive charge, yes, that multiplied by the amount of displacement that you have done, the differential displacement. Now if I'll have to calculate the work done for bringing it from infinity to that particular configuration of R, then I'll have to integrate it, yes, integrating it from infinity to that particular position of R, Q by 4 pi epsilon naught R dash square dr dash. So Q by 4 pi epsilon naught R dash. So basically upon integrating R power minus 2, I will obtain a R power minus 1 by minus 1, and minus 1 factor gets cancelled out, and finally we are obtaining okay, why have we taken a negative side? So work done by an external force will be obviously equal, okay fine, yeah, fine, great. So yeah, I'm basically integrating it, and I'm considering, okay, R at infinity ante the value is going to be 0, which means that the work done in bringing a unit positive charge from infinity to that particular position is going to be equal to my electrostatic potential. So by definition of the potential P, then obviously the potential at particular configuration R is going to be equal to Q by 4 pi epsilon naught R. Now I am writing it in terms of K, then it is KQ by R for a point charge, that is the electrostatic potential due to a point charge in its surroundings is going to be equal to KQ by R. Yes, so that's how I'm defining it. Now let's talk about equation 2.8. Equation 2.8 is true for any sign of charge Q. So it doesn't depend upon what are the charge Q, that basically we didn't impose any conditions on the charge Q, which means that it's going to be independent of the sign. So though we consider capital Q be greater than 0 in its derivation, so obviously we consider it to be in the derivation of we have calculated them, taken it to be calculated. That's what I said. It is not necessary that we will have to take the charge Q that you are taking to be equal to the like a positive charge. It is not necessary to be a positive charge. It can also be a negative charge as well. So for Q less than 0, the potential will obviously be less than 0, which means that work done by external force, we are obviously defining only for the external force. So the work done by the external force in okay, per unit positive test charge in bringing it from infinity to the point is negative. This is equivalent to saying that the work done by the electrostatic force in bringing that unit positive charge from infinity to that point P is positive. Wait a minute. Okay, so basically as we have taken the charge Q less than 0, which means a negative charge, the negative charge the potential is going to be negative, which means that the electrostatic force work done by electrostatic force is going to be positive for bringing it from infinity to the particular configuration P. Hope you are able to understand why, because the electrostatic force is exactly equal magnitude and opposite sign to the direction of the external force. That's what I'm trying to say. So that electrostatic force and the displacement from infinity to P are in the same direction. Okay, fine, great. Finally, we note that the equation 2.8 is consistent with the choice that potential at infinity to be 0. Okay, so basically equation 2.8, if I'm trying to calculate, I mean, okay, why are they doing this? So there's a figure 2.4 which shows the electrostatic potential and the electrostatic field. So basically both are inversely proportional to r and r square respectively. So as you can see, till a particular position, that is exactly at the potential at 1, yeah, at exactly r is equal to 1, the potential and fields are actually equal. And before that, the electrostatic field is going to be having a higher value than that of the electrostatic potential. And as r becomes lower than less than 1, the r square factor will become more lesser than 1 by r, which means that we'll obtain the electrostatic field to be less than the electrostatic potential in the subsequent movement. So basically how we are defining the electrostatic potential is that is the work done in bringing a unit positive charge. So potential energy பொறுத்த வரைக்கும் it was the work done in bringing a positive any amount of charge from infinity to that particular position P, which is equal to the difference in potential energy at position P minus that position infinity. Yes, for defining potential energy, I mean for electrostatic potential, we are considering a unit positive charge, which means that I am making something irrelevant of the charge and making it dependent upon the electric field. And electric field means ante it is going to be the work done in bringing a unit positive charge from infinity to that particular position P, which is the difference in potential energy divided by the amount of charge that you are bringing. Hopefully you understood this. Yes, these are certain important definitions. Moving down, we'll calculate the potential. We'll calculate the potential at a point P due to charge. Okay, so basically what do we know that due to a point charge is k q by r is the potential. So k is 9 into 10 power 9, q is 4 into 10 power minus 7, and the distance is basically 9 into 10 power minus 2. 9 factor gets cancelled, 10 power minus 2 factor gets to the numerator, it will become 10 power 11 into 10 power minus 7 into 4 is going to be equal to 4 into 10 power 4 volts. So we'll basically calculate potentials in terms of voltage, volts. So hence obtain the work done in bringing a charge of charge of point q. Does the answer depend on the path along with which the charge is brought? So basically work done is going to be equal to the amount of charge that you are bringing to that of multiplied by the potential difference between the 2 points. And if I'm considering potential at infinity to be equal to 0, then it is actually equal to q into potential at particular position, and that particular position the potential is going to be equal to the what we have calculated, that is 4 into 10 power 4, and the amount of charge, the charge's value is 4 into 10 power minus 7. So 16 into 10 power minus 3, is it so? Okay, am I missing something, brother? Oh, I'm sorry, it's actually they're given the charge to be 2 into 10 power. Okay, fine, great. So it's going to be 8 into 10 power minus 5. So as we have seen here, it doesn't depend upon the position, I mean it doesn't depend upon the path which we have taken, because potential itself is actually defined with respect to the potential energies, and the potential energies is obviously we have defined the potential energies only at certain positions like P and R, something like that. So which means that it is not going to be dependent on the path. Any arbitrary infinitesimal path can be resolved into two perpendicular displacements, one along the R and along perpendicular to the R. The work done corresponding to the later will be 0. So work done perpendicular to that of the R will be 0, it seems. Okay, is it so? So basically in that particular case scenario, we will have cosine of the angle between these two guys to be equal to 0, which means that the perpendicular component will be irrelevant in work. Moving down, potential due to an electric dipole. So now that we know that electric dipole has a dipole moment of the charge enclosed multiplied by the internuclear distances between the two. Yes, so that's what an electric dipole is, and its dipole moment is, and the total charge is going to be 0. It's characteristic by the dipole moment, which is q into 2a, in which direction from minus q to plus q. So we also saw that the electric field of a dipole at a point with position vector r depends not just on magnitude r, but also on the angle between r and p. So என்ன சொன்னோம், electric field of a dipole at a point with position vector r is not only dependent upon the distance or whatever the magnitude of r you have taken, but also the angle, whatever the angle is taken between the r vector and that of p vector. Why is it so? Actually, I think we wrote it yesterday, that is 2kp by r cube and minus kp by r cube. 2kp by r cube was the axial component and the minus kp by r cube was the equatorial component. Both will, one of them will be along the directions and another one Okay. So basically we are talking about the theta dependence, that is the angle dependence of potential, I mean whatever the dipole moment, no, electric field or angle dependence between the r bar vector and the momentum vector or dipole moment vector. Further, the field falls off at large distance, not as 1 by r square, typical field due to a single charge, but as 1 by r cube, which means that it's going to fall further faster. Yes. So we now determine the electric potential due to a dipole and contrast it with the potential due to a single charge. So basically what we are going to do is that we'll determine the potential due to a dipole and we'll make a comparative study with that of potential due to a single charge, which is k cube by r. Yes. So as before, we take the origin at the center of the dipole. Okay, fine, great. ஸோ நம்ம எப்போவுமே இந்த டைப்போல் டைப் ஆஃப் கான்ஃபிகரேஷன்ஸ்லாம் டீல் பண்ணும்பொழுது வில் கன்சிடர் டு பி த சென்டர் ஆஸ் த ஆரிஜின். எஸ், we now know that the electric field obeys the superposition principle. Since potential is related to the work done by the field, electrostatic potential also follows the superposition principle. அதாவது electrostatic field அப்படின்றது it is going to follow a superposition principle ante, and also the electric field, I mean the potential, it is related to the work done by the field. It is work done by the field in bringing or whatever. Yes. So which means that it is also going to be following superposition principle. So thus the potential due to dipole is the sum of the potentials due to charges capital Q and small, I mean capital Q plus Q and minus Q. So which means that potential due to capital Q is equal to K into capital Q by R, and potential due to minus Q is equal to K into minus Q by R, and R will be varying with respect to whatever the positions you are taking. As you have seen, you can see in this particular diagram. So in the diagram பொறுத்த வரைக்கும், just a second. Drink some water. Yes, or else you will be exhausted, you feel burnt. Okay, so as you can see in the diagram, we are having a configuration of a dipole with the origin to be at the center. So if I'm considering a point P from the origin, so basically from plus Q, let's say the distance is R1, from minus Q, let's say the distance is R2, then which means that the potential due to positive charge Q is going to be equal to KQ by R1. Potential due to minus Q is equal to K minus Q by R2. And since they are following the superposition principle, we'll take the magnitude to be equal to 1 by 4 pi epsilon naught times Q by R1 minus Q by R2. So where R1 and R2 are the distances of the point P. Okay, fine. Now by geometry. Okay, they are making use of geometry, it seems. Oh my god. R1 square is equal to R square plus A square minus 2AR cos theta. Why is it so? It's actually the addition law, that is the magnitude is equal to the root of R square plus A square minus 2AR cosine of angle between those two guys. And similarly R2 square is going to be equal to R square plus A square plus 2AR. Okay, so basically in case of plus Q, it is in the opposite sense, which means that I will have to consider the minus A vector. In the other way, I am considering the plus A vector. Is it so? Yeah, basically in the first case, the angle between the two vectors is obtuse, which means that obviously the cosine of the angles is going to be can be converted in terms of acute with a negative sign multiplied between before them. And similarly in the second case, we are having a acute angle, so which means that I can consider a positive sign. Hope you are able to understand here. R1 R square plus A square plus 2AR cos theta. sorry, r2 square is equal to r2 square plus equal to 2 a cos theta, and r1 square is equal to r2 r1 square plus a square minus 2a r1 cos theta, whatever, 2a cos theta, something like that. So which means that we take r much greater than a and retains the terms only up to the first order in a by r. Okay, so basically I'm taking r square factor common, and I'm considering a to be far lesser than that of r square. So it's actually the a square factors can be actually neglected. So r square times 1 minus 2a cos theta by r. So similarly, that is r1 square, and r2 square is equal to r square times 1 plus 2a cos theta by r, using the binomial theorem. So basically r1 square was this, r2 square was that, and we are making use of binomial theorem. What does that? So basically we are retaining the first order terms in a by r. Okay, what they are trying to do is that 1 by r1 is 1 by r times 1 minus 2a cos theta by r times r power minus 1 by 2, which is equal to 1 by r times 1 plus a by r cos theta. Wait a second. What they're trying to do is that basically we'll take the reciprocal and we'll take the square root. Plus 1 by r times 1 minus 2a cos theta by r whole power 1 by 2. R square also will obtain. Okay, so when I'm taking a reciprocal, yeah, fine, great. So making use of this guy, I'm basically obtaining 1 by r1 to be equal to 1 by r times 1 plus a by r cos theta, and for 1 by r2 it is equal to 1 by r times 1 minus a by r cos theta. Yes, so using equations 2.9 and 2.13 and p is equal to 2qa, we get v is equal to q by 4 pi epsilon naught 2a cos theta by r square. Wait a minute. So basically we are making use of the fact that the dipole moment is equal to 2qa, and we are making use of the equations of potential difference, potential at point P due to the positive charges going to be making use of superposition principle. 1 by 4 pi epsilon naught times q1 by r1 minus q by r1 minus q by r2. So basically it's a 1 by r1 minus 1 by r2 factor, and since we knew the values of 1 by r1 and 1 by r2, so I'm just substituting them. So it's basically q by 4 pi epsilon naught times 2a cos theta by r square. So since we knew that 2qa is equal to the dipole moment, so it's taken to be p cos theta by 4 pi epsilon naught r square. And since we knew that p cos theta is actually p dot r cap, so which means that p dot r cap kp dot r cap by r square. So okay, fine, wait. Cos theta component is basically the projection of p, that is the dipole moment vector along the radial vector, the radial vector along which we are calculating the distances. So that's why I'm considering p dot cos theta to be p cos theta to be equal to p dot r cap, because p dot r cap has a magnitude of p into 1 into cos theta, which is p cos theta itself. Yes, moving down, equation 2.15. So அதாவது என்ன நடக்குது, the potential is equal to 1 by 4 pi epsilon naught times kp times p dot r cap by r square, with r far greater than e. That's the considerations that we have taken. And equation 2.15 is as indicated approximately true only for distances large compared to the size of the dipole. Okay, it is only valid when we are considering the distances to be far greater than the dimensions of the dipole. So the higher order terms in a by r are negligible. That is, a square by r square terms are negligible. For a net pi point, for a point dipole at the origin, is, however, it is exactly the same. Okay, and the potential on the dipole axis where we are considering theta is equal to 0 or pi, the potential is going to be equal to kp by r square. Whereas in case of you know finally we are obtaining a concise equation upon making certain assumptions that along the axis is going to have this particular value, that is kp by r square. The positive signs for theta is equal to 0 and negative sign for theta is equal to pi. So the general term is that it's p cos theta by kp cos theta by r square. Yes. The important contrasting features of electric potential of a dipole from that due to a single charge are clear from equations 2.8 and 2.15. So the potential due to a dipole depends not just on r but also on the angle between the position vector r and the dipole moment vector p. So now it is actually considering considering the cosine of the angle between the p bar and r bar, which means that the potential is obviously dependent upon, as we have seen in case of field, அதே மாதிரி potential is dependent upon the angle between the r bar vector and the dipole moment vector. So the angle between position vector and dipole moment vector, it is however actually symmetric about p. That is, if you rotate the position vector about r about p, okay, keeping theta fixed, the points corresponding to p on the cone so generated will have the same potential as at p. Okay. If I'm keeping the theta constant and I'm just rotating the value, I mean whatever the configuration is, then the point at which I'm calculating the potential will remain the same. That's what they're trying to say. Is it so? It's such that the distance are also remaining the same. Okay, fine, great. The electric dipole potential falls off at large distance as 1 by r square, not as 1 by r. So it's 1 by r square concordance. Whereas in case of potential of point charge, it was kq by r. That is a 1 by r factor. We are having a 1 by r square factor in case of a dipole. So not as 1 by r. Characteristics of the potential due to a single charge. Okay. Now we are trying to concentrate on the potential due to a system of charges. So basically it's going to follow the system of charges with the position vector r1, r2, r3. The potential due on potential V1 at point P due to the charge is going to be 1 by 4 pi epsilon Q1 by R1P, where R1P is the distance between Q1 and P. Similarly, the potential V2 at P due to Q2 and V3 due to Q3 are given by this. So which means that by the superposition principle, the potential V at point P due to the charge, total charge configuration is the algebraic sum. I don't think potentials are actually dependent on the directions. Basically, we have defined it with respect to work done, which is a scalar itself, and a charge, which is also a scalar itself, which means that the whole of the system or the whole of the configuration is going to be scalar. Hence, by making use of superposition principle, it's going to be only the algebraic sum. Yes, so basically the net potential at the position P due to the system of charges is going to be the sum of the potential due to each and individual charges at that particular position, and the presence of one charge does not change the configuration of that of the other. So if we can have a continuous charge distribution characterized by a charge density rho of r, we divide it as before into small volume elements such as size delta V and carrying a charge rho delta V. So if at all, if I'm having a configuration of continuous charge distribution, let's say, which is having a density of rho that is varying with respect to r, then if I'm having to calculate the value of charge for let's say our differential element, then the amount of charge due to that particular differential element will be the whatever the volumetric density multiplied by the volume itself, and we then determine the potential due to each volume element, and then we'll sum it up all. Yes, for obtaining the potential due to the entire distribution. This is the sequence in which we will calculate the potential. அதாவது ஒரு பர்டிகுலர் ஒரு கொடுக்கப்பட்ட பாடினால, let's say there is a point P, let's say it's at my head, and if there is a body, the potential due to this particular body at that particular position will be calculated by making use of smaller differential volumetric elements or smaller differential linear charge elements, and integrating them for whole of the body. Yes, by making use of appropriate elements in the integration. So we have seen in chapter 1 that for a uniformly charged spherical shell, the electric field outside the shell is as if the entire charge is concentrated at the center. Thus the potential outside the shell is also given by kq by r, where q is the total charge and on the shell is going to be equal to 1 by 4 pi epsilon q by r, and that this implies the potential is constant inside the shell as well. The electric field inside the shell is 0. Although the electric field inside the shell is 0, this implies the potential is constant inside the shell. Why is it so? So basically the change in potential Wait a minute. So field is basically the amount of force acting on a unit positive charge, and if it is turning out to be 0, force is actually work done by R, and if the work done is itself 0, work done is basically the difference in potentials, and if the work done is itself 0, which means that difference in potential is 0, which means that at every position the potentials are going to be equal, and it will be equal to the potential at the particular position where there was the highest amount of potential, that was equal to at that particular R position, capital R position, that is at the boundary surface of the shell, that is k cube by capital R. Okay, fine, great. Next. Okay, so basically we have two charges, 3 into 10 power minus 8 coulomb and 2 into 10 power minus 8 coulomb, minus 2, which are located at 15 centimeter at one point on the line joining the two charges. The electric potential is 0. So electric potential is the sum of the potentials to the each individual charges. It is equal to kq by, let's say the total length of the, distance between them is 15 centimeter. If the distance at which the particular point where we are considering the potential to be 0 is, let's say, at the distance of R from one of the charges, let's say we are considering 3 into 10 power minus 8 coulombs, and then the remaining charge will be equal to 15 minus R into 3. Okay, that's going to be the distance for the 2 minus 2 into 10 power minus 8.5 joules. This means that the potential, sum of the potential, which is kq by R, kq1 by R1 plus kq2 by R2. We'll take a k factor common. Q1 is going to be equal to 3 into 10 power a minus 8 by R1. R1 is going to be equal to R plus minus of 2 into 10 power minus 8 by 15 minus R. So k into 10 power minus 8, 3 by R minus 2 by 15 minus R. R is equal to 15, no, 9 centimeter, which means that the other guy is going to be at 40. Okay, we will have another configuration as well. Figures 2.8a and b show the field lines of positive and negative point charges respectively. Okay, they are supposed to find. Give the signs of the potential difference Vp minus Vq, Vp minus Va. Okay, potential at Q will be lesser than that of potential at P, so Vp minus Vq will be obviously positive, whereas potential at A will be greater than that of potential at P, which means that Vp minus Vba will be negative. Vp is less negative and Va. Okay, moving down. Here is the sign of the potential energy difference of a small negative charge between Q and P and A and B. Here the sign of the work done by the external agency in moving a small negative charge from B to A. Sign of the work done by the external agency in moving a small negative charge from B to A. Okay. Force of repulsion and the charge velocity decreases and hence the magnetic energy decreases. Okay, now we are going to talk about equipotential surfaces. So an equipotential surface is a surface with a constant value of potential at all points on the surface. So let's say for a given single charge configuration, the equipotential surface will be a concentric spherical surface at a distance of r. Yes. So now the electric field lines for a single charge q are radial lines starting or ending at the charge depending on whether the q is positive or negative. Clearly the electric field at every point is normal to the equipotential surface passing through that point. This is true in general. For any charge configuration, equipotential surface through a point is normal to the electric field at that point. In general, for any charge configuration, the electric field is actually normal to that of the equipotential surface at that particular position. So proof of the statement is basically simple. Okay, so if the field were not normal to the equipotential surface, it would have had a non-zero component along the surface. To move a unit test charge against the direction of the component of field, work would have to be done. But this is in contradiction to the definition of an equipotential surface. There is no potential difference between any 2 points on the surface and no work is required to move a test charge on the surface. Okay. If they are actually equipotential, which means that there will be Vp minus Vq will be actually equal to 0. But what they are trying to say is that if at all if it is not normal, then there will be a component along the surface as well. So if there's a component along the surface, then obviously this particular component will be acting. Sorry, dude. Offer an alternative visual picture in addition to the picture of electric field lines around a charge configuration. Okay, so for a uniform electric field E, say along the x-axis, the potential surfaces are planes normal to the x-axis, that is the planes parallel to yz plane. Okay, for a uniform electric field E along the x-axis, the equipotential surface will be normal, that is the yz plane. Okay, the equipotential surfaces of a dipole to identical positive charges. Okay, fine, great. Now will be talking about the relation between potential and field. Yeah. So consider two closely spaced equipotential surfaces A and B with potential values V and V plus delta V, where del V is the change in potential in the direction of the electric field E. Let P be a point on the surface B. Del L is the perpendicular distance of the surface A from P. Okay, let P be a point on the surface B. Del L is the perpendicular distance of the surface A from B. Imagine that a unit positive charge is moved along this perpendicular from the surface B to surface A. So basically what's happening, I am considering two potential equipotential surfaces which are closely spaced. So let's say one surface has a potential V, then the other one will obviously have a differential change only, that is del V. And let's say there's a point P on the on the surface B, and del is the perpendicular distance of the surface A from B. Now we will imagine a unit positive charge is moved along this perpendicular from surface B to surface A against the electric field. So the work done in this process is mod of E times del L. Okay, mod of E times del L. Is it so? Why is it so? Because no. basically it's a unit positive charge layer, so the force can be actually equal to field itself, that is k cube by r square. So this work equals to the potential energy, potential difference is va minus vb. So v minus v del v is minus del v, so mod of E is equal to minus del V by del L. So since del V is negative, del V is minus of mod of del. So we can rewrite the equation as why del V is negative, brother. அதாவது என்ன சொல்ல வராங்க, basically for unit positive charge the work done is going to be equal to mod of E times del L, and actually I'm moving against the field, so which means that the potential, I mean the work done I'm going to do is going to be negative. So potential at del, I mean potential del V will be potential the farther distance will be less than, so which means del V is actually becoming negative, so which means the mod of E is gradient of del V, yes, del V by del L. Okay, so we thus arrive at two important conclusions concerning the relation between the electric field and potential. Electric field is in the direction in which the potential decreases steepest. Okay, potential difference, potential decrease ante inga steeper ante I think higher, which means that Va minus Vb is large enough அப்படின்றது சொல்ல வரோம், that is the work done is large enough, which means that electric field is in that particular direction it seems. So its magnitude is given by the change in magnitude of potential per unit displacement normal to the equipotential surface at the point. So basically the relationலேருந்து நமக்கு என்ன தெரிய வருகிறது என்றால், first of all the electric field magnitude is basically equal to the gradient along, I mean gradient of electric potential along that particular distance or whatever in which we are calculating. So electric field is actually in the direction in which the potential decreases the steepest. So the del V, if it is higher, I mean okay fine great, what else we will have, the magnitude is given by the change in magnitude of the potential per unit displacement normal to the equipotential surface at that particular point. Okay fine great. So potential energy of a system, potential energy of a system. So consider first the simple case of two charges q1 and q2 with position vector r1 and r2 relative to some origin. Let us calculate the work done in building of this configuration. Okay, this means that we consider an external agency to bring the charges to the positive to the given locations. Now we are trying to calculate the potential energy of a system of charges, whereas potential energy is defined as the work done in bringing a charge from infinity to that particular configuration. Now first case we will consider a system of two charges in which q1 and q2 are having position vectors r1 and r2 relative to certain origin. Let us calculate the work done in building of this configuration. This means that we consider the charges q1 and q2 initially at infinity and determine the work done by an external agency to bring the charges to that given locations. Suppose the first charge q1 is brought from infinity to point r1. There is no external field against which work needs to be done. So work done in bringing q1 from infinity is going to be 0. Yes, hope you are understanding what I am trying to say. There is no field because basically there is no field in this particular place, there is only completely vacuum. Now I am bringing a new charge q from infinity to a particular configuration. So which means that if there is no field, then obviously there will be no external work to be needed to be done, which means that we will have no work to be done. Now this charge produces a potential in the space, so there will be a field due to this particular charge, which means that there will be corresponding potential in accordance to with this particular charge. So V1 is equal to 1 by 4 pi epsilon naught times Q1 by R1P, where R1P is the distance of a point P in space from the location of Q1. From the definition of potential work done in bringing charge Q2 from infinity to the point R2 is Q2 times the potential to at R2 due to Q1. So basically work done is KQ by R times change in potential energy. From the definition of potential, work done in bringing charge Q2 from infinity to point R1 will be equal to the Q2 times the amount of potential that is present. Oh, ho, 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 ho. ஒரே ஒரு நிமிஷம். So basically potential என்பது என்னது? The work done bringing a unit positive charge from infinity to that particular configuration, which is equal to the change in potential energy divided by the amount of charge that you have taken in. And if I'm considering the potential energy at infinity to be equal to 0, that's basically UP by R. Or it can also be considered to be the charge multiplied by the amount of potential that is being present. Amount of field that is present over there. Field is basically KQ by R. Potential at R2 due to Q1. Something I'm unable to understand at this particular position. Let me just see this. So work done is actually equal to mod E dot del L. Yes, that is fine. But do we have a concordance between potential and wait a second, let me just once check. Potential due to a system of charges. Okay, in that particular position will be the summation. Yes, okay, that is fine. Okay, I think we had it over here. KQ by R, potential at point P due to the charge Q is this, and if I'll have to have the work done is basically equal to okay, work done in bringing unit positive charge will be equal to that of the potential அப்படின்னா work done in bringing some amount of charge will be equal to the potential multiplied the charge. Okay, fine, yeah. Oh yes, I'm able to understand it. So basically there's obviously certain amount of potential, which is actually the amount of work done in bringing a unit positive charge. Now that I'm bringing a Q2 amount of charge, which means that I will have to multiply this with the Q2 factor, and that's why I'm doing this. That is Q1 Q2 by R. That is the work done. Now since the electrostatic force is conservative, this work is stored in the form of potential energy. So whatever the work I'm doing, Q into V, that is actually stored in the terms of potential energy in that particular field. So I'm obtaining the potential energy of a system of two charges Q1 and Q2 is actually equal to KQ1 Q2 by R1 of 2. Obviously if Q2 was brought first to its present location and Q1 brought later, the potential energy U would be the same. Yeah, it is not dependent upon the amount of time that we have taken. So more generally, the potential energy expression equation 2.22 is unaltered whatever may be the charges are brought to the specified locations. பிகாஸ் ஆஃப் பாத் இண்டிபெண்டன்ஸ் ஆஃப் ஒர்க் ஃபார் எலக்ட்ரோஸ்டாட்டிக் ஃபோர்ஸ். அதாவது ஜென்ரலாக என்ன சொல்ல வராங்கன்னா, அந்த பொட்டன்ஷியல் எனர்ஜி அப்படின்ற எக்ஸ்பிரஷனே நம்ம எந்த வழியில் கொண்டு வரோம் இல்லை எந்த நேரத்தில் கொண்டு வரோன்ற முக்கியம் இல்லை, இனிஷியல் பொசிஷன் அண்ட் ஃபைனல் பொசிஷன்ன்ற மட்டும் தான், அதாவது கான்ஃபிகரேஷன்ற மட்டும் பேஸ் பண்ணி இருக்கிறது தான் இந்த எலக்ட்ரோஸ்டாட்டிக் பொட்டன்ஷியல் எனர்ஜி ஆஸ் வெல். பிகாஸ் இட் இஸ் டியூ டு த ஃபேக்ட் தட் the work done in this particular electrostatic field அப்படின்றது is going to be path independent. So equation 2.22, that is true for any sign of q1 and q2. If q1 q2 is greater than 0, the potential energy is positive. This is as expected, since for like charges electrostatic force is repulsive and the positive amount of work is needed to be done against this force to bring the charges from infinity to find a distance apart. Whereas in case of an attractive type of force, we will have to do the opposite thing, that is the positive amount of work is needed against this force to take the charges from the given location to infinity. That is, a negative amount of force will be needed to take the charges from infinity to that particular configuration, which means that it's going to be a negative path. Yes, so the potential energy is going to be negative for in case of q1 q2 in the opposite signs. So equation 2.22 is easily generalized for a system of any number of point charges. Let us calculate the potential energy of a system of 3 charges q1 q2 q3 at locations r1 r2 r3. So to bring q1 first from infinity, no work is required. Now next, to bring q2 from infinity to r2, we have to do the potential, where that is the potential is actually the work done in bringing unit positive charge. So I am having a unit positive charge or work done, I am multiplying it with the charge of that particular configuration, that is q. So q2 times v1 at r2 position configuration is 1 by 4 pi epsilon naught times q1 q2 by r12. And now that we have two charges at this particular configuration, to bring about a third charge, we will have the fields of both of them, which will means that there will be field due to 1 and 2, and field will be actually equal to the, according to superposition principle, will be the algebraic sum of this particular fields, or whatever, q1 by r1p plus q2 by r2p, and then we'll have to multiply it with q3 factor. Then the total work done in assembling the charges is q1 q2 by r12 plus q1 q3 by r13 plus q2 q3 by r23. So again, because of conservative nature of the electrostatic force, the path of independence of work done, the final expression for u is independent of the manner in which configuration assembled. As we can see, it is only depending upon the distances, that is the configuration, and the amount of charges that is being present, that is the q1 q2 q3. So the potential energy is a characteristic of the present state of configuration, not the way the state is achieved. Okay, they are emphasizing it again and again, which means that we will have, it is something important to be noted and to be remembered of. Okay, so 4 charges are arranged at the corners of a square ABCD of side D as shown in figure 2.15a. Find the work required to put together this arrangement. Whoa. A charge, find the work required to put together this arrangement. So basically the work depends on the final arrangement of charges, not on how they put together. They calculate the work needed for one way of putting the charges A, B, C and D. Suppose first charge plus q is brought at A, and then the charges minus q plus minus q are brought to B, C, D respectively. The total work needed can be calculated in the steps. So first things first, the work done needed to plus q charge to a particular position A is actually B0. The work done needed to minus q to B when positive q is at A is that this is given by charge at A multiplied by the electrostatic potential at B. Now the work done is needed to bring a point C, when it will be equal to the sum of the potentials at that particular position multiplied by the amount of charge which we are going to bring, and similar thing will have to be done for the fourth position as well. Now that we are done with all that things, we will have to just consider and add them all. The work depends only on the arrangement of the charges and not how they are assembled. By definition, this is the total electrostatic energy of the charges. Okay, students may try calculating the same work or energy by taking charges in any other order they desire and convince themselves with the energy. So it is really important for the calculation part to be done properly, such that there is not any mistakes being done. Next, what they are asking is that a charge q0 is brought to the center E of the square, the 4 charges being held fixed. How much extra work is needed to do in this particular fashion? So basically it is the potential multiplied due to this particular configuration at that particular position E multiplied by the amount of charge that we are going to bring. So basically hence no work is required for bringing any charge to point E. Okay, the electrostatic potential at E is clearly 0, since potential due to A and C is cancelled and B and D is cancelled. Okay, then great. Now we are talking about potential energy in an external field. Okay, what is that? Okay, in section 2.7, the source of the electric field was specified, the charges and their locations, and the potential energy of the system of those charges are determined. In this section, we ask a related but a distinct question: what is the potential energy of charge q in a given field? Let's say I have given the field, I have not specified the amount of charges being present, which means that only the field is actually required. And if I have given the field, then how much amount of potential energy is present for that particular small charge q? So this question was in fact the starting point that led us to the notion of the electrostatic potential. So electrostatic potential கான காரணகர்த்தாவே இவர்தான். But here we address the question again to clarify in what way it is different from the discussion in section 2.7. Okay, so the main difference is that we are now concerned with the potential energy of a charge or charges in an external field. So before that we calculated, okay fine, there's not much in, okay, let's read this. External field E is not produced by the given charges whose potential energy we wish to calculate. Yes, so E is produced by some external forces to the given charges. External forces may be known, but often they are unknown or unspecified. What is specified is the electric field or the electrostatic potential V due to the external forces. We assume that the charge small q does not significantly affect the sources producing the external force. So basically இந்த பர்டிகுலர் கான்ஃபிகரேஷனை பொறுத்த வரைக்கும் இதுக்கு முன்னாடி 2.7ல் பார்த்தபோது எப்படின்னா we had a charge and அந்த சார்ஜோடைய பொட்டன்ஷியல் அட் அ பர்டிகுலர் பொசிஷன் இதெல்லாமே நம்ம ஸ்பெசிஃபை பண்ணோம். ஆனால் இந்த பர்டிகுலர் கேஸில் we cannot do that. We are having only the fields. The field or a source can be known, but in the most cases unknown. We are considering the charge then about which whose potential energy we are going to calculate to unaffect that source. Yes, that is the first assumption that we are going to make. This is true if q is very small and the external sources are held fixed by certain unspecified forces. Even if q is finite, its influence on the external forces may still be ignored in the situation when very strong forces far away at infinity produce a finite field E in the region of interest. Note again that we are interested in determining the potential energy of a given charge q in the external field. No, okay. We are not interested in the potential energy of the sources producing the external electric field. We are not interested in the potential energy of the sources producing the external electric field. We are only considering about the small q charge. The external electric field E and the corresponding electric potential V may vary from point to point, and by definition, the potential at a point P is the work done in bringing a unit positive charge from infinity to that particular point P, and we continue to take potential at infinity to be 0. Thus, the work done in bringing unity positive charge from infinity to that particular point P is, and an external field is going to be equal to the Q multiplied by V. So that's going to be the amount of work done, and the work done is stored in the form of potential energy for that particular guy, which means that if the point P has a position vector r related to some origin, then the potential energy of q at that particular position r is going to be equal to the amount of q multiplied by v. Yes, so where v of r is the external potential at particular point. Okay, thus if an electron with the charge q is equal to E is equal to 1.6 into 10 power minus 19 coulomb is accelerated by a potential difference of delta V is equal to 1 volt, it would gain an energy of q into delta V, that is 1.6 into 10 power minus 19 joules. This unit of energy is defined as 1 electron volt, that is 1 electron volt is actually the okay fine, wait a minute. The amount of energy gained by a charge, an electron, in a region of potential difference of 1 volt is actually 1.6 into 10 power minus 19 joules, which is a unit of energy defined as 1 electron volt or 1 ev, which is equal to 1.6 into 10 power minus 19 joules. The units based on ev are most commonly used in atomic, nuclear and particles physics. Okay fine, which we will use in okay fine, great. Now we will calculate the potential energy of a system of two charges in an external field. So now next we ask the question, what is the potential of a system of two charges? First we calculate the work done bringing the charge q1 from infinity to r1. Work done in this step is q1 into v times r1, v of r1. Next we consider the work done in bringing q2 to r2. In this step work is done not only against the external field but also against the field due to q1, which means that the work done on q2 against the external field is actually equal to the q2 times v at r2, where work done on q2 against the field due to q1 is equal to q1 q2 by 4 pi epsilon times r12. Yes, where r12 is the distance between q1 and q2. We have made up these equations by the principle of superposition. We will basically add up the work done on q2 against the two fields C and that due to q. So which means that we will basically multiply q2 times v of r2 plus q1 q2 by 4 pi epsilon times r12. Thus, the potential energy of the system is equal to the total work done in assembling the configuration, and that particular configuration is actually, total work in assembling the whole of the configuration, which is Q1V plus Q2V times plus Q1 Q2 by 4 pi epsilon delta R1 R of 112 R1 of 2. So example 2.5, determine the electrostatic potential of a system consisting of two charges on microcoulomb and minus 2 microcoulomb with and with no external field placed at minus 9 cm 0 and 9 cm 0 and 0. So basically we have two charges placed apart at 18 cm apart. Now I will have to calculate the electrostatic potential of a system of charges with no external field. If there is no external field, the first so basically first of all we will consider the work done in bringing one particular charge, and since there is no external field, which means that bringing the particular charge to that particular position is going to be 0, and then the field produced by this particular charge will be equal to kq by r, and the matter of interest is at a distance of 18 cm, which means the 9 into 10 power minus 9 in 9 into 10 power plus 9 times q is equal to 7 into 10 power minus 6 times divided by 18 cm 18 into 10 power minus 2 is going to be my field. So that is the work done bringing a unit positive charge. Now the potential energy is basically the work done bringing a positive charge, whatever the amount of charge that we are giving from infinity to that particular position, and that is going to be equal to the amount of field that is present multiplied by the amount of charge that is we are going to bring, that is minus 2 into 10 power minus 6. So basically 10 power 9 factor gets cancelled over here, this factor gets cancelled over here, so it's a minus 7 into 10 power 5 into 10 power minus 6 is a minus 7 and minus 0.7. The amount of electric potential, electrostatic potential energy of a particular system of charges. How much work is required to separate the two charges infinitely away from this is basically the amount, same amount of, okay, they are asking the work is basically U2 minus U1, which is equal to U2 itself. U1 is going to be equal to 0, so which means that it's a negative of the thing. That's what I was about to say actually. Okay, and then we have, suppose that the same system of charges is now placed in an external field. E is equal to A times 1 by R square, where A is 9 into 10 power 5. What would be the electrostatic energy of this configuration? U is equal to 1 by 4 by epsilon Q1 Q2 by R, which is, okay, suppose that the same system is now placed in an external electric field, then obviously we will have QV1 plus Q2V1 plus Q2V2 Q1V of R1 plus Q2V of R2 plus Q1 Q2 by 4 by epsilon naught R of 1 2. Okay, that's it for an external electric field. Now we'll calculate the potential energy of a dipole in an external electric field. So consider dipole with charges Q1 is equal to plus Q, Q2 is equal to minus Q, placed in a uniform external electric field. As seen in the last chapter, in a uniform electric field, the dipole experiences no net force, but the torque is experienced, and the expression for torque is actually equal to dipole momentum multiplied with the cross product with the electric field. Suppose an external torque is applied in such a manner that it neutralizes this torque, and it rotates in the plane of paper from angle theta naught to theta 1 at an infinitesimal angular speed and without angular acceleration. Now we are entering into the angular aspect of what we are going to do, since we are calculating it with respect to the torques. So basically என்ன சொல்றாங்க, it is taken from a theta naught configuration to theta 1 configuration without movement, that is without any acceleration occurring, angular acceleration occurring. So which means the amount of work done in this particular process is going to be equal to the net torque applied by the external force, external field in the configuration of theta multiplied for every differential change in the angular displacement from theta naught configuration to theta 1 configuration, which is Pe sin theta d theta, which is equal to Pe cos theta naught minus cos theta 1. Yes, so basically it is the work done. Now this particular work will be stored as the potential energy of the system. We can then associate the potential energy U theta with an inclination theta of the dipole. Similarly to the other potential energies, there is a freedom in choosing the angle where the potential energy U is taken to be 0. Now what I am going to do is that taking theta naught is equal to pi by 2. Theta naught pi by 2 will be considered to be the place at which I will consider the potential to be 0, which means that the potential energy stored in this particular field in changing the configuration from let's say pi by 2 configuration to that of any other whatever the configuration is going to be equal to minus P cos theta. Yes, so why have we taken pi by 2 to be the configuration perpendicular? Basically that is Okay, let's see why they have done this. So the expression can alternatively understood also from the equation 2.29. You can apply the equation 2.29 to represent the system of charges plus q and minus q. So the potential energy expression is that u dash theta is equal to q times v of r1, v at particular position r1 minus v at particular position r2 minus of that of the particular position of q square by 4 pi epsilon naught time 2a, where r1 r2 that denote the position vectors of plus q1 minus q. Now the potential difference between the r1 positions R1 R2 equals to the work done in bringing a unit positive charge against the field from R2 to R1. Okay, so the displacement parallel to the force is 2a cos theta. Thus VR1 minus VR2 is equal to minus E into 2a cos theta. Wait a minute. They are actually confusing me. Antarctica, Penguin, penguin, penguin. Okay, this actually the last guy is confusing me. Let me just check it once. So basically I'm trying to calculate the potential energy configuration with respect to angular whatever the things I'm going to take in consideration. So that's going to be equal to Pe cos theta naught minus cos theta 1. Yes. So that's going to be the amount of work done by the external field, external force in doing a torque against exactly equal torque against the sky in an infinitesimal speed. So also the expression cannot so basically the potential energy expression is can be concluded as q into v of v at position r1 minus v at position potential at position r2 minus q square by 4 pi epsilon naught times into 2a. So that is the potential energy at that particular configuration u theta, u dash theta. So u dash theta is actually equal to minus Pe cos theta. Basically the q of v, q delta v is the work done, and work done is basically q into 2a. So that's q into 2a, that's hypermomenta. Displacement is gonna be 2a cos theta. So q into E is the amount of force that is acting, and the displacement that's going to be occurring is 2a cos theta. Yes, so that is q into delta v. Basically q into delta v is the amount of potential, I mean that is the work done. Work done in terms of force can be given as QE into 2a cos theta. Okay, that is fine. So basically minus PE cos theta. Why I have taken minus PE cos theta? It is basically V of R1 minus V of R2 is minus EA into 2a cos theta. So basically I have calculated the value of potential energy at a particular configuration. Now what and this particular guy is a constant, which means that constant at a particular position can be cancelled out when we are calculating the potential difference in which this particular things are getting cancelled out. Okay, now that we have completed the first type, the potential energy field, the relation between potentials and fields, இந்த அளவெல்லாம் முடிச்சதுக்கப்புறம் now we are entering the electrostatics of the conductors. Oh my god, conductors. God damn it. This is huge. Okay, fine. Let's learn them. But before that, we'll have a small break. In metallic conductors, these charge carriers are electrons. And in a metal, the outer electrons, that is the valence electron, part away from their atoms and they are free to move. These electrons are free within the metal but not free to leave the metal. The free electrons form a kind of gas. They collide with each other and with the ions and move randomly in different directions. In an external field, they drift against the direction. Of field. The positive ions made up of the nuclei and the bound electrons remain held in the fixed positions. In electrolytic conductors, the charge carriers are both positive and negative ions, but the situation in this case is more involved. The movement of the charge carrier is affected by both the external electric field and also by the so-called chemical forces, which we learn in the next chapter, that is current electricity. So we shall restrict our discussion to the metallic solid conductors. Let us note important results regarding electrostatics of conductors. So basically we have certain important results to be noted in case of electrostatics of conductors. So first things first, inside a conductor, electrostatic field is 0. Consider a conductor neutral or charged. There may also be an external electrostatic field. In the static situation, when there is no current inside or on the surface of the conductor, the electric field is 0 everywhere inside the conductor. Rather, when there is no current inside or on the surface of the conductor, the electric field is 0 everywhere inside the conductor. This fact can be taken as the defining property of a conductor. A conductor has free electron. As long as the electric field is not 0, the free charge carriers would experience force and drift. In the static situation, the free charges have so distributed themselves that the electric field is 0 everywhere inside. The electrostatic field is 0 inside a conductor. The first thing is that the electrostatic field is 0 inside a conductor. Basically, a conductor has free electrons in its movement, and as long as the electric field is not 0, the free charge carriers will experience a force and drift. And in a static kind of a situation, basically we'll have the conductor's electrons to be accumulated in such a fashion that the net electrostatic field is going to be equal to 0. At the surface of a charged conductor, electrostatic field must be normal to the surface at every point. அதாவது சார்ஜ் கண்டக்டரோட surface, the field will be normal to the surface. So electrostatic field is not normal to the surface. It would have some non-zero component. Free charges on the surface of the conductor would then experience a force and they will move. And static situation, therefore, the electric field should have no tangential component. Thus, the electrostatic field at the surface of a charged conductor must be normal to the surface at every point. So for a conductor without any surface charge density, field is 0 even at the surface. Okay. The interior of a conductor can have no excess charge in the static situation. All we are considering is in the static situation, okay? So a neutral conductor has equal amounts of positive and negative charges. When the conductor is charged, the excess charge can reside only on the surface in the static situation. This follows from the Gauss's law. Consider any arbitrary volume element V inside a conductor. On the closed surface S bounding the volume V, electrostatic field is zero. So அதாவது let's say I'm charging the conductor and the excess of charge is residing only on the surface on the static situation. Static situation the charges can be residing only on the surface, and this follows from the Gauss's law. Why? Let's consider an arbitrary volume element V inside the conductor on the closed surface S bounding the volume element V. Electrostatic field is zero. Thus the total electric flux through S is zero. The total electric flux through S is zero. Hence by Gauss's law there is no net charge enclosed by S, but the surface S can be made as small as you like. That is, the volume V can be made vanishingly small. This means there is no net charge at any point in the conductor. Irappa, ஒரு நிமிஷம். There is no net charge enclosed by S, but the surface S can be made as small as we like. Okay. Oh, okay. It's actually following from the first property. So first property நம்ம என்ன சொன்னோம், inside a conductor the electrostatic field will be zero. Now if I am considering a Gaussian surface inside the conductor, since the electrostatic field is zero, I am considering only a differential amount of volume of a surface. So which means that in that case scenario, the closed surface is bounding the volume V, the electrostatic field is zero, the electric flux through S is zero. Hence by Gauss's law there is no net charge enclosed by S. But the surface S can be made as small as you like. The volume can be made vanishingly small. This means there is no net charge at any point inside the conductor. Okay. Electrostatic potential is constant throughout the volume of the conductor and has the same value on its surface. So this follows from results 1 and 2 above. Since the electrostatic field is zero inside the conductor and has no tangential component on the surface, no work is done in moving a small test charge within the conductor and on its surface. So அதாவது potential is constant throughout the volume of the conductor and has the same value as inside on its surface. And from 1 and 2 we knew that the electrostatic field inside the conductor is zero, there is no tangential component, which means there is no work is done, which means the potential difference is actually equal to the amount of work done, and if the work done is turning out to be zero, which means the potential difference is zero, which means that every potential are equipotential surfaces, and hence the result, if the conductor is charged, the electric field normal to the surface exists. This means the potential will be different for the surface and a point just outside the surface. So in a system of conductors of arbitrary size, shape and charge configuration, each conductor is characterized by a constant value of potential, but this constant may differ from one conductor to the other. In a system of conductors of arbitrary shape, size, each conductor is characterized by a constant value of potential, but this constant may differ from one conductor to the other. Okay, fine, great. Let me just have a small break as of now. Yeah. Yeah, let's just continue. I'm sorry, I took a break. I don't think I'll take any more breaks till completing this chapter. So going down, now we'll talk about the fifth property of conductors, that is the electric field at the surface of a charged conductor is going to be equal to sigma by epsilon. So why is it so? Let's see what we are trying to obtain over here. To derive the result, choose a pill box, a short cylinder, as the Gaussian surface about any point P on the surface. The pill box is partly inside and partly outside the surface of the conductor. It has a small area of cross section del S and negligible height. Just inside the surface, the electrostatic field is 0. Just outside, the field is normal to the surface with magnitude E. Thus, the contribution to the total flux through the pill box comes only from the outside cross section. So this equals to plus minus E into del S. Positive for sigma is greater than equal to 0 and negative for sigma less than 0. Since over the small area del S, E may be considered a constant and E and del S are parallel or anti-parallel, the charge enclosed by the pill box is equal to sigma del S. So by using Gauss's law, E del S is equal to sigma mod of sigma del S by epsilon naught, which is where we got obtain E is equal to mod of sigma by epsilon naught. So basically நம்ம என்ன பண்ணுறோம், I'm considering a conductor in which I have a particular Gaussian surface which is half size of, which is obtaining shape of a small pill box. So இப்போ என்ன நடக்குதுன்னா, just inside the surface the electrostatic field is 0 because basically that particular surface is enclosing a conductor. Conductor oda inner part, it's actually going to be equal to 0, the electrostatic field is 0, and outside the conductor, just outside, the field is normal to the surface with magnitude E. Thus the contribution to the total flux through the pill box comes only from the outside cross section. Okay, and let's say the particular pill box is having the outside configuration, the area is going to be del S அப்படின்ற பொழுது, in case of Gauss's law, we'll basically have integral E bar dot del S, and the del S is integral for that particular small Gaussian surface is going to be E del S itself. It's going to be equal to the amount of charge enclosed. The amount of charge enclosed will be equal to the charge density, aerial charge density multiplied by the amount of area it is enclosing, the whole divided by epsilon naught. The del S factor is getting cancelled out, and the electrostatic field from Gauss's law we obtained to be equal to sigma by epsilon naught. Including the fact that electric field is normal to the surface, we get the vector relation equation 2.35, which is true for both the signs of sigma. For sigma greater than 0, electric field is normal to the surface outward, and if it is less than 0, it's going to be inward. Now electrostatic shielding. Consider a conductor with a cavity with no charges like the inside the cavity. So let's say I have a conductor with a cavity and there is no charges inside the cavity. A remarkable result is that the electric field inside the cavity is 0. Okay, whatever be the size and shape of the cavity and whatever be the change on the conductor and external field in which it might be placed. So let's say I'm considering a conductor with a cavity. Okay, fine, great. And there is no charges inside the cavity, and the remarkable result is that the electric field inside the cavity is 0. Okay, whatever be the size and shape of the cavity, it's gonna be the charge on the conductor and the external field in which it might be placed. We have proved a simple case of this result already. The electric field inside a charged spherical shell is 0. So the proof of the result for shell makes use of the spherical symmetry of the shell, as we have seen in chapter 1. So basically the potential due to all the other guys will be cancelled out each other, which means that the field will be actually turn out to be equal to 0. So it is due to the symmetrical part, but the vanishing of electric field in the cavity of a conductor is, as mentioned, is basically a very general result. A related result is that even if the conductor is charged or charges are induced on a neutral conductor by an external field, even if the conductor is charged or an external field, if it is getting some amount of whatever the charges are induced, all charges reside only on the outer surface of the conductor with cavity. Okay, so the proofs of the results noted in figure 2.18, as you can see, whatever will be the charge in the field configuration outside any cavity in the conductor remains shielded from outside electric influence. The field inside the cavity is always 0. So whatever be the charge and the field configuration outside, Any cavity in a conductor remains shielded from the outside electric influence. This is known as the electrostatic field shielding. The effect can be made use of in protecting sensitive instruments from outside electrical influence. So figure 2.19 gives a summary of the important electrostatic properties of a conductor. So basically, in a case of a conductor, inside a conductor, the electrostatic field is going to be 0. And if at all, if I am having a cavity as well, no matter what is the configuration outside the conductor, whatever the field is present outside the conductor, whatever the charges are present outside the conductor or on the surface of the conductor, the field inside the conductor is going to be equal to 0. And the potential is going to be equal to the surface potential, that is V0 or whatever. And yes, and that's what we call as the electrostatic shielding. The effect can be made use of protecting sensitive instrument. Okay, fine, great. So we have certain important properties of electrostatic. Okay, so basically the electric field at a particular surface is going to be equal to sigma by epsilon naught n cap. Yes, and the electric field inside the conductor is going to be equal to 0, since the charge present inside the conductor is going to be 0, and the potential is going to be equipotential to that of the surface itself. And whenever there is a cavity present inside the conductor, the electric field inside the conductor is going to be 0, since there is no charge present in that particular conductor, no matter what is the amount of charge that is present on the outer surfaces. Yes, so basically we have example over here. A comb run through one's dry hair attracts small bits of paper. Why? Because the comb gets charged by friction, the molecules in the paper gets polarized. The molecules in the paper gets polarized, resulting in a net force of attraction. If the hair is wet or if it is in a rainy day, friction between hair and the comb reduces and the comb does not get charged. Okay, so ordinary rubber is an insulator, but special rubber tires of aircraft are made using slightly conducting. Why is it this? To enable them to conduct charge produced due to friction to the ground, as too much of electrostatic electricity accumulated may result in a spark and resulting fire. Okay. Vehicles carrying inflammable materials usually have metallic ropes touching the ground during motion. Inflammable materials have metallic ropes touching the ground during motion, similar to that of B. Okay. A bird perches or on a bare high power line and nothing happens to the bird. A man standing on the ground touches the same and gets a fatal shock. Only when there is a difference in potential. Okay, so potential difference in the current flow the bird is not having any amount of different potential, it seems. So moving down, we are talking about dielectrics and polarization. Dielectrics are non-conducting substances. In contrast to conductors, they have no charge carriers. Recall from section 2.9 what happens when a conductor is placed in an external electric field. So what we saw that the free charge carriers move and charge distribution in the conductor adjusts itself in such a way that the electric field due to the induced charges opposes the external electric field within the conductor. So as you can see in the first figure 2.20, let's say I am having a conductor which is neutral in nature, is experiencing an electric field E0 from left towards the right. So obviously the negative charge carriers are basically will move against the electric field, and it will be induced near the end to which the electrostatic field is present, and it will move away. The positive charge will move away from that particular end, and then there will be a net electric field will be produced due to the polarization of charge, the separation of charges, that is E induced. Yes, which will be in the opposite direction to that of the external electric field which we are applying. This happens until in the static situation, the two fields cancel each other and the net electrostatic field is 0. In a dielectric, this free movement of charge is not possible. It turns out that the external field induces dipole moment. By stretching or reorienting the molecules of dielectric. The collective effect of all the molecular dipole moments is net charges on the surface of dielectric, which produce a field that opposes the external field. Unlike in a conductor, however, the opposing field is so induced it does not exactly cancel the external field. It only reduces it. அதாவது என்ன சொல்ல வராங்க, நம்மளுடைய நார்மல் கண்டக்டர் அப்படின்ற கேஸில் பார்க்கும்பொழுது we had the charge separation occurring, but in case of a dielectric there is nothing called as charge separation, but there will be a net dipole moment that will be induced. So it will basically occur due by stretching or reorientation. The collective effect of all the molecular dipole moments is net charges on the surface of the dielectric, which produce a field that opposes the external field. Okay, it produces a field and it opposes the electric field, and unlike in a conductor, the opposing field does not exactly cancel the external field, it only reduces it. The extent of the effect depends on the nature of the electric. To understand the effect, we need to look at the charge distribution of a dielectric at the molecular level. So let's see what's happening in case of a dielectric at a molecular level. The molecules of a substance may be polar or non-polar. In a non-polar molecule, the centers of positive and negative charges coincide. The molecule then has no permanent dipole moment. Examples of non-polar molecules are oxygen, hydrogen molecules, which, because of their symmetry, have no dipole moment. On the other hand, a polar molecule is the one in which the centers of positive and negative charges are separated. So, such molecules have a permanent dipole moment, and ionic molecules such as HCl or H2O are examples of polar molecules. Yes. So, in an external electric field, the positive and the negative charges of a non-polar molecule are displaced in opposite directions. The displacement stops when the external force on the constituent charges of the molecules is balanced by the restoring forces. The non-polar molecule thus develops an induced dipole moment. So non-polar molecule பொறுத்த வரைக்கும் there will be movement of the positive and negative charges, but at the same time there will be restoring forces occurring at the same time as well, which will lead to the formation of a dipole moment. The dielectric is said to be polarized by an external field. அதாவது ஒரு non-polar molecule பொறுத்த வரைக்கும் it is becoming polarized, which means that the positive and the negative centers are actually separated due to the presence of electric field, but they are not completely moved away due to the restoring forces acting between them. I think that's what it's actually happening over here. In case of non-polar molecules, in case of polar molecules, okay, we consider only the simple, okay, the dielectric is said to be polarized by the external field. We consider only the simple situation when the induced dipole moment is in the direction of the field and is proportional to the field strength. Okay, we will consider a simple situation when the induced dipole moment is in the direction of field. Okay, and is proportional to the field strength. Substances which are for which this assumption is true are called linear isotropic dipole. Okay, the induced dipole moments of different molecules add up, giving a net dipole moment of the dielectric in the presence of external field. The induced dipole moments of different molecules add up, giving a net dipole moment of the dielectric in the presence of an external field. Okay. So a dielectric with polar molecules also develops a net dipole moment in an external field, but for a different reason. In the absence of any electrical field, the different permanent dipoles are oriented randomly due to thermal excitation, so the total dipole moment will be zero. When an external field is applied, the individual dipole moment tend to align with the field, and summed over all the molecules, there is a net dipole moment in the direction of external field, that is the dielectric will become polarized. The extent of polarization depends on the relative strength of two mutually opposite factors, the dipole potential energy, okay, in the external field tending to align the dipoles with the field, and the thermal energy tending to disrupt the alignment. So basically the polarization depends on two factors. One is the potential energy in which the alignment of the dipole is occurring, and the other one is the disruption of the particular alignment due to thermal energy. So there may be in addition the induced dipole moment effect as for non-polar molecules, but generally the alignment effect is more important for polar molecules. Okay. Non-polar molecule பொறுத்த வரைக்கும் there will be something called as induced dipole moment, but generally the alignment effect is more important for polar molecules. Okay. Thus in either case, whether polar or non-polar, a dielectric develops a net dipole moment in the presence of an external field. For a polar molecule, dielectric, polar or non-polar எதுவாக இருந்தாலுமே ஒரு net dipole moment வந்து create ஆகுதுன்னு சொல்கிறாங்க. The dipole moment per unit volume is called the polarization, denoted by P. And for linear isotropic dielectrics, the polarization is actually equal to the amount of electric field, directly proportional to the amount of electric field which is present, and the proportionality constant Xe is what we call as the electrical susceptibility of the dielectric medium, so which is a constant characteristic for a given dielectric. So moving down, it is possible to relate Xe to the molecular properties of the substances, but we shall not pursue that here. Okay, fine, great. So the question is, how does the polarized dielectric modify the original electric field? So let us consider for simplicity a rectangular dielectric slab placed in a uniform external field E not parallel to two of its faces. So basically for simplicity I am considering a rectangular slab, okay, there is a uniform electricity, okay, electric field, okay, E naught that is parallel to two of the faces. The field causes a uniform polarization P of the diameter. Thus, every volume element del V of the slab has a dipole moment P del V in the direction of the field. The volume del V is macroscopically small but contains a very large number of molecular dipoles. Anywhere inside the dielectric, the volume element del V has no net charge. Okay. The volume element del V is macroscopically small but contains a very large number of molecular dipoles. Anywhere inside the dielectric, the volume element del V has no net charge. Since it has a dipole, though it has a dipole moment, the net charge will be zero because the positive charge of one dipole sits close to a negative charge adjacent. However, at the surfaces of the dielectric, normal to the electric field, there is evidently a net charge density. Normal to the electric field on the surface will have a net charge, okay, fine. As seen in figure 2.23, the positive ends of the dipole remain unneutralized at the right surface. Okay, the balanced charges are induced charges due to the electric. Thus, the polarized dielectric is equivalent to two charged surfaces with induced surface charge density, say sigma p and minus sigma p. Clearly, the field produced by these surface charges opposes the external field. The total field in the dielectric is thereby reduced from the case when no dielectric is present, where we should note that the surface charge density plus minus sigma p rises from bound, not free charges in the dielectric. Okay. That was a lot. I think it would be better if we have a recap. The non-polar molecule, polar molecule ரெண்டுமே சொல்லியிருக்காங்க. Non-polar molecule basically the centers of positive and negative charges will be at the same position. Okay, so basically what will happen is that in case of the negative, in presence of an external field, yes, the non-polar molecule will develop an induced dipole moment because due to the fact that the positive and negative charges tend to separate. At the same time, there will be a restoring forces acting as well. So an induced dipole moment is in the direction of the field and is proportional to the distance. Substance for which this assumption is true. So induced dipole moments of the different molecules add up giving a net dipole moment of the dielectric in the external field. Dielectric with polar molecules also develops a net dipole moment in an external field, but for a different reason. In the absence of any external field, the different permanent dipoles are oriented randomly by the thermal. So the total dipole moment is zero. When an external field is applied, the individual dipole moment tend to align with the field. And somewhere all the molecules there is a net dipole moment in the direction of the external field, that is the dielectric is polarized. The extent of polarization depends on the relative strength of the two mutually opposite factors. Okay, so the first factor is that the dipole potential energy in the external field, which will tend to align the dipole with the field, and there will be a thermal energy that will be disrupting it, and there will be in addition there will be an induced dipole moment effect for a non-polar molecule. Generally, the alignment effect is more important, and basically the amount of polarization that is developing in the particular dielectric, whether it is a polar or non-polar in the presence of an external field, it is given by this particular dipole moment per unit volume. That's what we call as the polarization, which is denoted by P. And for linear isotropics, it's actually for dipole moment is equal to electrical susceptibility multiplied with electric field at that particular position. Okay. Okay, fine. No, it's not. No. So how does polarized dielectric will modify the original electric field? So now that we have seen what polarization has done, I mean how polarization is done, then we'll see what it can do. So we'll consider for simplicity a rectangular dielectric slab placed in a uniform external field parallel to two of its faces. Okay. The field causes a uniform polarization P of the dielectric. Okay. It will cause a uniform polarization will occur, and let's say the every volume element LV of the slab has a dipole moment P delta V in the direction of the field. The field volume delta V is macroscopically small but contains a very large number of molecular dipoles. Anywhere inside the dielectric, the volume element delta V has no net charge. Okay. This is because the positive charge of one dipole sits close to the negative charge of the adjacent dipole. So basically it has obtained a net dipole moment of P delta V. Basically the amount of polarization occurring in the amount of dipole present in a given volume of given net volume is what we call as polarization, and polarization multiplied by delta V will give me the amount of dipole moment in that particular position, and there will be, though there's a dipole moment is present, the total net charge will be equal to 0. Surface of the dielectric normal to the electric field, there is evidently net charge density. Okay. So fine. Moving on towards capacitors and capacitance. So a capacitor is a system of two conductors separated by an insulator. Okay. The conductors have charges Q1 and Q2 and potentials V1 and V2. Usually in practice, the two conductors have charges capital Q and capital minus capital Q with the potential difference V, which is equal to V1 minus V2 between them. We shall consider only this kind of a charge configuration of the capacitor. Even a single conductor can be used as a capacitor by assuming the other at infinity. The conductors may be so charged by connecting them to the two terminals of a battery. Capital Q is called charge of the capacitor, though this is in fact the charge in one of the conductors. The total charge of the capacitor is going to be 0. The electric field is in the region between the conductors is proportional to the amount of charge capital Q. That is, if the charge on a capacitor, let's say, is double, the electric field also will double at every point. This follows from the direct proportionality between the field and the charge implied by the Coulomb's law and superposition principle, which means that if I'm doubling the charge, then the amount of field present in that particular region will also be doubled. So now the potential difference V is the work done per unit positive charge. Yes, in taking a small discharge from the conductor 2 to 1. Consequently, V is also proportional to Q, and the Q by V is a constant ratio known as the capacitance of the conductor, which is independent of Q or V as stated below. Above, the capacitance depends only on the geometrical configuration such as the shape, size and separation of the system of the conductors. And the SI unit of capacitance is 1 farad, which is 1 coulomb per volt. 1 farad is 1 coulomb per volt. A capacitor with fixed capacitance is symbolically shown as this, with one of the variable capacitance as that. So the equation 2.38 shows that for a large value of C, V is small for a given Q. So this means a capacitor with a larger capacitance can hold large amount of charge Q at relatively smaller value of V. If there is a relatively smaller value of potential difference between the two conductors forming a capacitor, then the amount of charge stored will be, the total amount of the capacitance will be actually higher. So this is of practical importance. High potential difference implies strong electric field around the conductors. A strong electric field and ionize the surrounding air and accelerate the charges so produced to the oppositely charged part, thereby neutralizing the charge on a capacitor place at least partly. In other words, the charge of the capacitor leaks away due to the reduction in insulating power of the intervening medium. Okay, so the maximum electric field that a dielectric medium can withstand without breakdown is called its dielectric strength. Separation between conductors of order of 1 cm, the field corresponds to a potential difference 3 to the 10 power 4 volts between the conductors. Hence, the electric field do not exceed the breakdown limits. Put differently, there is a limit to the amount of charge that can be stored in a given capacitor without significant leak. So அதாவது ஒரு கொடுக்கப்பட்ட கெப்பாசிட்டர் to store a large amount of charge without leaking, the capacitance should be high enough so that the potential difference, hence the electric field, do not exceed the breakdown limits. Whereas in the other case, there is a limit to the amount of charge as well that can be stored in a given amount of capacitor without leaking. In practice, a farad is a very big unit. The most common units are this. Key element of most as circuits with the important functions we will describe in chapter 7. Okay. So basically we are going to talk about parallel plate capacitor, where we will be dealing with two large plane parallel conducting plates separated by a small distance. We first take the intervening medium between the plates to be vacuum. The effect of a dielectric medium between the plates is discussed in the next section. Let A be the area of each plate and D be the separation between them. The two plates have charges Q and Q. Since D is much smaller than the linear dimension of the plates, okay, we can say use the result on electric field by an infinite plate sheet of uniform surface charge density. So plate 1 has a surface charge energy sigma is equal to Q by A, and the charge plate 2 has a minus sigma surface charge density. And the electric field on the outer region above plate 1 will be equal to sigma by 2 epsilon naught minus sigma by 2 epsilon. Why is it so? Urugi, Urugi, Konari, Milo, Yani, Mili, Urugi, Konari. Sigma by epsilon. Okay, that's going to be the electric field between the region. So the direction of electric field is from the positive to the negative plate. Thus, the electric field is localized between the two plates and is uniform throughout. For plates with finite area, this will not be true near the outer boundaries of the plates. The field lines bend outward at the edges, an effect called the fringing of the field. So the electric field is localized between the two plates and is uniform. Plate 20, if it has a finite area, this will not be true near the boundaries because there will be something called as the fringing of the field. By the same token, sigma will not be strictly uniform in the entire plate. So E and sigma are related by the equation 2.35. So equation 2.35, let me just show it to you, brother. Yes, E is equal to sigma by epsilon naught, mod of sigma by epsilon naught. And what they are trying to say over here is that thus the electric field is localized between the two plates and is uniform throughout. For plates with finite area, this will not be true near the outer boundaries of the plates. The field lines bend outward at the edges. Okay, fine, great. However, for D square far less than A, these effects can be ignored. And for sufficiently far from edges, the field there is this. And now for uniform electric field, the potential difference is simply the electric field line times the amount of distance between them, which is QD by epsilon T. The capacitance will be equal to Q by D. So it's epsilon naught A by D for a parallel plate capacitor, which as expected depends only on the geometry. And the typical values, okay, for capacitance, you can check that 1 farad is actually equal to 8.8 number minus 9. 30 kilometers in length and breadth. Effect of dielectric on a capacitance. With the understanding of the behavior of dielectrics in an external field development section 2.10, let us see the capacitance of a parallel plate capacitor modified when a dielectric is present. As before, we have two large plates, each of area A separated by distance small d. The charges on the plates is plus or minus q, corresponding to the charge density plus minus sigma. Sigma is equal to q by A. And there is vacuum between the plates, then the electric field intensity is going to be equal to sigma by epsilon naught. So that's what we have derived. And the potential difference V naught is actually equal to epsilon naught times D, and E naught times D. The capacitance E naught is equal to Q by V, which is equal to epsilon naught dA by D. Now consider next a dielectric insert between the plates fully occupying the intervening region. The dielectric is polarized by the field, and as explained in section 2.10, the effect is equivalent to two charged sheets at the surface of the dielectric normal to the field with surface charge densities sigma p and minus sigma p. So there will be polarization occurring, and at the one end there will be sigma p amount of charge separation, and the other end there will be minus sigma p amount of charge separation. The electric field in the dielectric then corresponds to the case when the net charge surface charge density on the plates is plus minus sigma p. The plates is sigma minus sigma p. Just a second. So net electric field is actually equal to the charge density multiplied by, okay, the net electric field between the region is going to be equal to sigma by sigma p by epsilon naught. Okay, fine. Why is it so? From Gauss's law, we came to know that electric field due to the external force is going to be equal to sigma by epsilon naught from Gauss's law, and due to the dielectric polarization is going to be minus sigma p by epsilon naught. And since both of these are opposing in nature, we'll just subtract them, and then the electric field is going to be sigma minus sigma p by sigma polarized by epsilon naught, and that multiplied by d will give me the amount of that will give me the potential difference across the plates. Okay, and for linear dielectrics we expect sigma p to be proportional to net electric field. Okay, proportional to sigma, and we can write புரியல. Sigma minus sigma p is directly proportional to sigma, and the proportionality constant is equal to 1 by k, which is defined for a particular dielectric. K is a constant characteristic of a dielectric. If k is greater than 1, which means that sigma minus sigma p will be less than sigma, and greater than sigma. Then we have V is equal to sigma d by epsilon naught times k. Sigma by epsilon naught சரி. இப்போ பேசிக்கலி நமக்கு என்ன தெரியும், எலக்ட்ரிக் ஃபீல்டு இஸ் கோனா பி ஈக்குவல் டு சிக்மா பி பை எப்சிலான் நாட், and V is equal to ED, and since this is also equal to sigma by k, so sigma minus sigma p by epsilon naught times whatever the distance in between them, that's equal to sigma by k epsilon times d, and which is q a e epsilon naught q a k epsilon times d, that is equal to the potential difference. And since we know that q is equal to cv, and that is v is q by c, so epsilon naught a by d times k is the amount of capacitance when I am inserting a new dielectric. So where if at all, if epsilon k is called the permittivity of the medium and denoted by epsilon. So epsilon naught k is the permittivity of a medium, which is epsilon, which means that dielectric constant, which is the permittivity, relative permittivity, is actually equal to the epsilon naught by epsilon minus epsilon naught, which is the dielectric constant of the substance. So for vacuum, epsilon is equal to 1. The permittivity of the vacuum, yes, as remarked before, it is clear that K is greater than 1. Why is it so? Because epsilon is greater, 2.46 and 2.41, K is equal to C by C naught. Thus, the dielectric constant of the substance is the factor greater than 1 by which the capacitance increases from its vacuum value when the dielectric is inserted fully between the plates of capacitor. So, we arrived at equation 2.54. For the case of parallel capacitor, it holds true for any type of capacitor and can in fact be viewed in general as a definition for the dielectric of a substance. So, dielectric of a substance is the dielectric constant of a substance. Okay, we have electric displacement. We have introduced the notion of dielectric constant and arrived at equation 2.54 without giving the explicit relation between induced charge density sigma p and the polarizing. Okay, let's move. Basically, we are entering the combination of capacitors. It's actually a relatively easier topic. It's not that difficult to do. Mm, so basically, 1 by C effective is equal to, I'll just remember the results. Okay, 1 by C effective is equal to 1 by C1 plus 1 by C2 plus 1 by C3 in case of uh, what's that guy? Series combination. Series combination, and then in case of series combination, the current flowing will be the same. That is, the amount of charge that is deposited will be the same. By making use of that factor, we will be deriving this, and then what we will obtain is that the net potential drop across every capacitor will be equal to q by c1 plus q by c2 up to how much ever the amount of charge you have taken. Yes, q by cn. So the capacitors in parallel, for parallel plate capacitor, the potential difference will be equal, which means that the amount of charge deposited, the effective capacitance will be the sum of individual capacitances, and the amount of charge deposited on each plate will be equal to Q effective will be Q1 plus Q2 plus Q3 will be given Q. Okay, fine, great. So energy stored in a capacitor, I think we are done with this one. We do not have Van de Graaff generator, right? Energy stored in a capacitor. So capacitor, as we have seen above, is a system of two conductors with charge plus Q and minus Q. To determine the energy stored in the capacitor, okay, am I supposed to know the derivations as well? It's actually Q square by 2C or half CV square. Yeah. Okay, fine, let's see the derivation as well. So energy stored in a capacitor. A capacitor, as we have seen above, is a system of two conductors with charge plus Q and minus Q. To determine the energy stored, consider initially two uncharged conductors 1 and 2. Imagine next a process of transferring charge from conductor 2 to conductor 1 bit by bit, so that at the end conductor 1 gets charge capital Q. Okay. By charge conservation, conductor 2 will have minus Q. In transferring positive charge from conductor 2 to conductor 1, work will be done externally, since at any stage conductor 1 is at a higher potential than conductor 2. To calculate the total work done, we first calculate the work done in small step involving transfer of an infinitesimal amount of charge. Consider the intermediate situation when the conductors 1 and 2 have the charges Q dash and minus Q dash respectively. At this stage, the potential difference V dash. Okay, so the differential amount of work done is equal to V dash multiplied by the differential amount of charge that we are basically supplying, that is equal to Q dash by C times del Q dash. So del W is equal to, since del Q dash can be made as small as we like, okay, what they are trying to do is that we are taking a 1 by 2C times Q dash plus del Q dash the whole square minus Q dash whole square. Okay, why is it so? These guys are confusing me. Okay. Okay, I'm not getting into the derivation. If at all, if it is required, then we'll get into this. So the final result is that the amount of charge energy stored will be equal to half CV square, which is equal to Q square by 2C. The electrostatic force is conservative. The work is stored in the form of potential energy. For the same reason, the final result for potential energy is also independent of the manner in which the charge configuration of the capacitor is built. So when the capacitor discharges, the stored up energy is released. It is possible to view that the potential energy of the capacitor is stored in the electric field between the plates. To see this, consider for simplicity a parallel plate capacitor and separation D. Okay. So the energy stored in the capacitor will be half Q square by 2C, which is A sigma square by 2 into W by epsilon. Okay. And E is equal to sigma by epsilon naught ante the energy stored in the capacitor U is equal to half epsilon naught E square times VAD. Note that AD is the volume of the region between the plates. The energy density will be equal to half epsilon naught E square. Okay, fine, great. Anti-graph generator இல்லைன்னு நினைக்கிறேன். By means of a moving belt and instead of brushes, charge is continuously transferred. Okay. Okay, now then we'll have certain exercises, and definitely today I'm not going to skip the exercises. But before that, we have the summary. We'll just see them. So basically, the electrostatic force is a conservative force work done by an external force in bringing a charge q from a point r to a point p is what is Vp minus Vr. That is the difference in the potential energy of the charge q between the final and the initial points. Potential at a point is the work done per unit charge in bringing a charge from infinity to that point. Potential at a point is arbitrary to within an additive constant. Okay, so since it is the potential difference that will be physically significant, if potential at an infinity is chosen to be 0, potential at a given point is okay, q by r. The electrostatic potential at a point is position r due to a point dipole of dipole moment is p dot r by k p dot r by r square. Okay, fine. For a charge configuration q1, q2 up to qn, the position of the r1, r2 up to rn, the potential at a given point. An equipotential surface is a surface over which the potential has a constant value. For point charge, concentric spheres centered at location of the charge or potential equipotential surfaces. Okay, the electric field at a point is perpendicular to the equipotential surface, and the electric field is in the direction in which the steepest decrease of potential. Steepest decrease in potential. Okay. Potential energy stored in a system of charges is the work done in assembling the charges at their location. So for a system of two charges given by 1 by 4 pi epsilon times q and q by r1 of 2, potential energy of a charge q in an external potential is equal to q times v of r. The potential energy of a dipole moment p in a uniform electric field E is minus p bar dot d u r, dipole moment dot u r. Electrostatic field E is 0 in the interior of a conductor just outside the surface of charged conductor. E is normal to the surface. Okay, capacitor system. Okay, great. Yeah. So let's get started for the questions, but before that let me just have a small break.